Good day and welcome back. This is the much anticipated first part of the discussion on differentiation formulas. And as a reminder of where we currently stand, when it comes to calculating derivatives, we only have the definition of the derivative. As of now, that statement won't be true in a few minutes, but we only have the definition of the derivative. So that is, we can calculate this function f prime x as being the limit as h approaches 0 of the difference quotient. And let me just note that there's also some equivalent notation. Instead of writing f prime of x, we occasionally, when convenient, will denote that as being the derivative of f of x, which is symbolically d dx. That is, differentiate the function f of x with respect to the variable x. And this is what we think of as being the definition of the derivative. And something that you have to be very careful of is as you are working through assignments, whether they're their homeworks or exams, if a problem asks you to use a definition of the derivative, you must go back to this limit of the difference quotient in order to receive credit for the problem. Now, if we do not specify that you have to use a definition of the derivative, it turns out that there are some rather convenient differentiation formulas. And I say convenient in the sense that always going back to this definition of the derivative and having to calculate what can sometimes be a tedious or maybe even slightly annoying limit is rather cumbersome. So we do want to be more efficient if that's possible. So the first differentiation formula we're going to introduce is what is the derivative of a constant, irregardless of what that constant c actually is. And before just writing this down, let me give you a little bit of graphical intuition. So if we are thinking about the function f of x equals c, well, graphically, if I think of c as being a positive quantity, the graph would be this curve y equals c, a horizontal line. And recall that the value of the derivative at a point is going to correspond to the slope of the tangent line there. So if I happen to pick my favorite value, let me just call it x, and you go up to the curve. When you draw the tangent line at that point, you just get the graph of the function itself, this horizontal line. So f prime of x, which would be the slope of this tangent line, is 0. So the derivative of any constant will always be 0, regardless of the constant that you have. And let me just kind of note that, we've seen why this is true from a graphical perspective, but we could also see why this is true quite easily using the definition of the derivative. So if f of x is equal to c, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. But if we think about this function f of x equals c, regardless of the input that we substitute in, you always get c as your output. So this would be the limit as h approaches 0 of c minus c over h. Well, c minus c is equal to 0, and 0 over h is equal to 0. So it ends up being the limit of a constant, which is simply that constant. And that is, the derivative of any constant is always going to be 0, regardless of what that constant is. And when it comes to our differentiation formulas, there should be some reasoning or explanation that can convince you that the formula is true, which would always involve going back to the definition of the derivative. And we won't do that for every one of our differentiation formulas. We'll just do it for a couple to kind of illustrate why they are true. Now, one of the most common rules that you will use the most throughout your calculus experience, literally hundreds of times, is something called the power rule. The power rule tells you that if n is any number, then the derivative of x to the n is going to be nx to the n minus 1. So how I think about this in terms of words is that the power n comes down front, and the new power is one less than previously. And I don't want to go through and try to explain why this is true, in general, but let's go ahead and just look at a very specific case to give you some intuition as to why this is true. So let's go ahead and just verify that this is true in the case where n is equal to 2. And let me first just kind of note to the side how we could do this with the power rule. So if we were to use the power rule, not the definition of the derivative, which we've been asked to do, we want to differentiate x squared. So this would correspond to the n value being 2. So that power 2 comes down front, and the new power is 1 less than it previously was. So that 2 is n minus 1. So we have 2x. And hopefully when we use the definition of the derivative, we will come up with that same function. So using the definition of the derivative of x squared is the limit as h approaches 0 of the difference quotient. So that would be f of x plus h minus f of x all over h. And of course we need to put this in terms of our specific function. So f of x is x squared. So f of x plus h is going to be the quantity x plus h squared minus x squared over h. And as usual, we cannot simply plug in h equals 0. That would force us to divide by 0, so not a good thing. But algebraically, we should see a very clear path. We can expand out the x plus h squared. That is, in the numerator, we would have x squared plus 2xh plus h squared. Then we have minus the x squared and all over h. So positive x squared, negative x squared. Note, we still can't just simply substitute in 0, but what we can do is factor an h out of that quantity in the top. So if we pull out an h, we would have a 2x plus h left over, dividing by h. The h's cancel. What remains as a function in h would be a polynomial. So you could either use the substitution property or continue on with the limit laws. I think it's simpler to just reference the substitution property, so that is what I will do. Replace that h with a 0, and we are left with 2x. And no, that's not surprising. It's exactly what we were expecting to happen. So this isn't a proof in general for the power rule, but it's just verifying that it's true in one instance, when n is equal to 2. So we now have this wonderful new differentiation rule, the power rule. And that allows us to quickly and conveniently differentiate x to the n, where n is any number. Note how much quicker it was to use the power rule versus the definition of the derivative. It's exactly what we've been working towards. With that in mind, I have two functions below that we would like to differentiate. What I would like you to do is to pause the video, take all the time that you need, and differentiate these two functions, making extensive use of the power rule. Okay, hopefully you have paused the video, you've taken a few minutes, you've calculated some derivatives, and now you're sticking around just for fun to make sure that your work matches up with mine. So when it comes to using the power rule, we need to have x to a power. If I want to differentiate square root of x, the key is to rewrite it so that it's in a form suitable for the power rule. So it's x to the 1/2, and if we compare that with the power rule, we're thinking n is 1/2. What the power rule tells us is that the derivative of x to the 1/2 will be 1/2 comes down front, and then x raised to the power 1/2 minus 1. So we are simply applying this formula above with the n value being played by 1/2. And we could leave it in this form and that would be the derivative, we'd be good to go, but differentiating the square root of x is something that we encounter frequently, so I want to go ahead and just algebraically simplify this a bit. So this would be 1/2 x to the minus 1/2. And recall, if you have x raised to a negative exponent, that's equivalent to dividing that quantity x with a positive exponent. And this ends up being 1/2 1 over the square root of x. And just to summarize this as conveniently as possible, because as mentioned we will encounter it frequently, the derivative of the square root of x is 1 over 2 square roots of x. You are more than welcome to use this formula whenever we encounter it, which we will frequently. The second function also needs a bit of manipulation so that we can use the power rule. So the first thing we would have to do is take that x squared that's being multiplied by everything on the right and distribute it through. So we could think of this as x cubed plus x to the 5/2. And just to make sure there's no confusion whatsoever, let me just note kind of a quick property of exponents that we've used. If you have x to the a times x to the b, you add those exponents together, x to the a plus b. So for example, if you had something like x to the 1/2 times x squared, that would be x to the 1/2 plus 2, which is x to the 5/2. Now that we've written it out, it becomes pretty quick and efficient to differentiate. So if we use the power rule term by term, so the derivative of x cubed, we're thinking power rule with n equals 3. So the power 3 comes down, the new power is 1 less. Similarly, if we want to differentiate x to the 5/2 using the power rule, the n value is 5/2. So that power 5/2 comes down front, and the new power is 1 less. And note, 5/2 minus 1 is 3/2. So the more you use this power rule, the quicker and efficient it will be to calculate derivatives. For the first example, I wrote out the n value, but after we've worked through enough of these, it will hopefully become almost second nature. Now, something you might be wondering is, we've used a rule that we haven't quite discussed yet. To differentiate this function f, I took the derivative of the first plus the derivative of the second. And that really is a more general rule of differentiation, and we will hit on that in our next video. So stay tuned and take care.